In this video, we'll talk about different population models that fit into this idea of autonomous equations. So one of the most common ways these equations are used in modeling is with population models, because in general, the population of a species doesn't depend explicitly on the exact time when it's happening. Yes, there's like seasonal changes and stuff, but in terms of simple models for this, we're going to assume that the rate of change of population does not depend on time explicitly. It just depends on what the population is at that current moment. And this exact idea, only depending on the population present, gives rise to an autonomous equation. So there's three main models that are used for populations in different contexts. The first is the simplest one, that's just exponential growth. dp dt is some growth rate times p. You can solve this explicitly, it's separable, and get what you would get out of that there. That's just going to grow forever. It only has one equilibrium solution at 0, and as long as it's positive, it takes off and it grows upward forever. The second is what's called logistic growth. And that looks something like dp dt is some rate times p times 1 minus p over k, where k here is the carrying capacity of the environment. If you sketch out a phase line for this one here or look at the actual equation, you'll see this has two equilibrium solutions. It has one at p equals 0, which is unstable, and one at p equals k, which is stable. What that means, if your population is between 0 and k, you're going to flow upwards to this carrying capacity level out there. If your population is too high or it's above k, you're going to fall downward until you hit k and then stabilize there. The point being is the environment can't support that many individuals in a population. The population has to drop down to stabilize with the environment. And then our third model that adds on this previous one is a threshold model. This adds one extra term here. So dp dt is some rate times p times 1 minus p over k times p over t minus 1. The additional component here is t, which is a threshold population. This sort of takes the role of the population that is the minimum value that need to be in the population for it to continue to survive. So if the population drops below t, as in you're under this threshold, the population dies off as time goes on. So this now has three equilibrium solutions. It has one at p equals 0, which is now stable, p equals t, which is unstable, and p equals k, which is stable again. So if you are between 0 and t, t is unstable, pushes you away, pushes you down towards 0. If you're between t and k, you're going to be flowing upwards towards k and stabilize at the carrying capacity. And if you're above k, you'll fall down to the carrying capacity. Now with these models and equations, it's interesting to ask questions about when the population hits certain values. And unfortunately, for a lot of these, we can't solve these out by hand. So only the simplest two models, maybe the first two discussed above, for exponential growth and logistic models, can be solved by hand. So it's possible in these cases to get the actual numbers as to when the population hits certain values or when the population reaches a certain amount of individuals. That can all be done by hand for these two models. For anything more complicated, we're not able to solve it out by hand. Even that threshold model, it would involve solving a cubic equation, which is not something you can always do to isolate the variable that you want. So in that case, we have two options. We have just discussing general behavior, which you can do with phase lines and things like that, or using numerical models to approximate the solution. This is really why numerical methods are so important, because there are a lot of different ways we can write that we can't solve out by hand. We want this data about when things hit certain values. And the only way we can really get that is using numerical methods like Euler's method or something more complicated to get the solution approximation that way. That's the idea of these exponential growth models, these population models as autonomous equations, and how we can discuss them and try to talk about their solutions as those of autonomous equations.